The Lineweaver-Burk plot by Bridget Baird. Imagine you are a soccer player running as fast as you can. At first you get faster as you push harder, eventually you hit top speed. Enzymes work the same way. The reaction speed increases with more enzyme until they reach max speed. This graph is called the Michaelis-Menten curve. At first, when substrate is added, it's like giving the player more energy, and the enzyme speeds up quickly. But eventually, all the enzyme's active sites are busy and can't go any faster. This top speed is called the Vmax. We can estimate the Vmax being around 10, as we can see here. The Km, which is the substrate concentration at half the Vmax, also known as the effort or energy available at half of the max running speed. We see that right here, the Vmax we're saying is 10, so we go to 5, we go over here. Over here would be the estimate of Km. The issue with this is as the curve flattens out, it's very hard to see the values. So this would give us an inaccurate Vmax, as we can see it's not even at 10, which would give us an inaccurate Km. To make things easier, we can use the Lineweaver-Burk plot. We just take the Michaelis-Menten equation right here, and we turn it into the reciprocal. This is also called the double reciprocal plot. As you can see over here, it's 1 over velocity, which is just like being 1 over running speed, and over here, 1 over substrate concentration, which is just like being 1 over energy exertion, if we're still talking about it in terms of a soccer player running. If we take this reciprocal equation and we break it up a little bit, it's easier to see that it is in y equals mx plus b format, turning this into the straight line. We can see over here that this would be the slope of the line, Km over Vmax. If we want values such as max running speed, also known as Vmax, or the level of exertion at half Vmax, also known as substrate concentration at half Vmax, Km, right here we can look at the y-intercept. The y-intercept is 1 over Vmax. The x-intercept over here is -1 over Km. This makes it way simpler and more efficient in finding Vmax and Km. For example, if we look at enzyme catalase, which protects cells by breaking down hydrogen peroxide, water, and oxygen. If we look at the Michaelis-Menten curve, trying to find the Vmax, we would have to take an estimate here, and then which then in turn inaccurates the Km. But if we look over here, to get the Vmax, we can look at the y-intercept, and we know that it's the reciprocal of the Vmax. And if we want to know how strongly it binds to the substrate, we can find the x-intercept, as we know that it's -1 over Km. Think of the Michaelis-Menten curve like tracking a soccer player's running speed, but with a wavy, hard-to-read chart. The Lineweaver-Burk plot is like lining up all the times, drawing a straight line, easily being able to see her max speed and being able to see the effort she exerts at half her max speed. Both are the same data, but the straight one makes the pattern way easier to understand. Even though the Lineweaver-Burk plot is really useful, it does have some downsides. Because of inverse values, the points tend to cluster together. Points from low substrate levels have a bigger effect, which can make small mistakes look really big, as well as important values such as Vmax and Km often lie on the outside of measured data, so scientists have to estimate. It's less accurate than newer methods that use computers and graph types. Because of that, scientists today mostly use it for teaching or quick checks, not for super precise calculations. So the Lineweaver-Burk plot doesn't change how the enzyme works, it just changes how we see it. By turning curvy enzyme data into a straight line, scientists can easily find key values like Vmax and Km. It's simple, but a powerful way to understand how enzymes work, just like tracking top running speed of a soccer player.